So the rate of nucleation can be obtained by doing this integral. And if the nucleation barrier, free energy around the barrier is short, and then in terms of the height of the barrier and the curvature around that barrier, curvature of free energy around number of particles at the critical size being NC, we can do the calculation easily with the paper and pencil. The answer turns out to be this is KNC, the forward rate constant, which depends upon the size of the critical nucleus. And then this is the nucleation barrier, e to the minus F dagger by KT. And there is a prefactor which also depends on temperature and the curvature, which I'm going to write it to be F double prime at NC. I'll put a modulus, because when you have a maximum, the curvature is negative, right? So I have to take the modulus of that. Divided by 2 pi kBT power half. Okay, where I can write this F double prime, second derivative NC modulus is equal to negative D square Fn by Dn square evaluated at N is equal to NC. Okay, that's the definition of that. So therefore now we have a clean expression, right? This is called, right? This is called classical nucleation theory. This expression. Okay. Let's go back and look at what it means. Right? I already told you for 3D, for D is equal to 3, I told you that F dagger goes like 1 over delta G squared, right? Quench depth squared. In fact, I purposely plotted here, right? F dagger goes like this. So your F dagger diverges, becomes extremely large for quench depth being small. So this is delta T for quench depth being small. What happens then is when quench depth is small, F dagger is very large, infinity, very large number. When F dagger is very large, E to the minus a large number will become negligible. So the nucleation rate is 0, essentially 0. Nothing will happen, right? Nucleation rate will be really 0. Okay. This means if I were to plot nucleation rate as a function of temperature, and here is my TC, nucleation rate will be 0 here. Essentially, nothing will happen because F dagger becomes very large and E to the minus large number goes to be 0. So nothing will happen here. Right. So only for deep quenches, when the temperature is much below TC, then it becomes small. If this becomes a small, then F dagger is, no, when delta T is large, F dagger becomes small, then it's a reasonable number. Then you'll have nucleation taking place. So if you do a shallow quench, nothing will happen because that's what I'm talking about, extreme metastability, very long-lived metastable state. So you need to go to a much lower temperature in order to see the nucleation process take place, right? Please contrast this with spinol decomposition. In spinol decomposition will be spontaneous. Fluctuation will take place right away. But here, right, at what wavelength fluctuation takes place, it depends upon quench depth. But here, the whole process of nucleation, you have to go to deeper, sufficient deep quench. And that is dictated by this F dagger, which in turn is dictated by your form that you write down. Your form you write down for free energy. Okay, and this is kind of a universal description. Okay, that is the nucleation process. And how does the growth take place? Right? For growth, I'm going to be simply extremely simple to make a statement. Okay, so for the growth is going to take place only if for R greater than R sub C. Right? Equivalently, number of particles is greater than number of particles or number of molecules above the critical value. So R, right? Then only nuclei grow. Otherwise, they don't. They'll dissolve back. Right? Then I can monitor the ray R as a function of T. R is a radius, right? Radius of this droplet that is growing as a function of time. Or you can also equivalently number of particles, number of molecules in this droplet as a function of time. This grows like this, square root of T for early time. Okay, and T is equal to 1/3, T power 1/3 for later times. For very, very late times, it goes like T. And you have seen this before, right? You have seen T to the 1/3 at late times and T for very late times. Remember, I'll remind you again. We saw that here. Remember, this is Km, it's a reciprocal of the size of your fluctuation, right? Km, the early stage of spinol decomposition, right? It is independent of time. Then you have Km going like negative 1/3 power. That means the domain size is growing like time power 1/3 plus 1/3, and then plus 1. We call this to be Lifshitz slice of the region. This is a hydrodynamic region. That's what we say. So what we see is for the nucleation growth, also you see the same behavior as in spinol decomposition in the late stages. In the early stage, the mechanism is different. The kinetic law is different. Here, it is independent of time, the early stage, but for our nucleation growth, it is square root of T. Okay. So in the early times, let me write it down here. For early times, spinol decomposition and nucleation growth are have different time evolution. Have different time evolution. For later times, they are similar. Okay? You cannot distinguish. At later times, you cannot distinguish between spinol decomposition and nucleation growth. Okay, that stops the kinetics of a phase separation. Right, we talked about, right, that there are two mechanisms again. Let me remind you again, I think, let me see, I think went back here. Where did I go? Yeah, for example, right, one mechanism, spinol decomposition, if you do this, you go through this process, but if you go into metastable state, right, you go into the other process. Metastable case, that's the nucleation growth. Oops, sorry. We can find out for you again. Yeah, I think we went through this right here, right? So this is, this is the metastable state. We have nucleation growth. In an unstable region, right? This is the way, right? In an unstable region, you have spinal decomposition. Please contrast this with what we talked about today. Contrast that picture with this picture. That's the nucleation growth. Okay. All right. I'll like to take a 1 minute break for you to think through a little bit. And then what I want to say while you are thinking, I like to emphasize if you think about like, okay, one molecule comes here and adds on to this to give me this nucleus N, then I make one more molecule come in to make a bigger droplet. Now the question is, how do those molecules come? How do they move around? What is the dynamics of this? How do they move in solutions? How do molecules move in solutions? And that's what we're going to talk about. So next long chapter, right, a long session, series of lectures would deal with polymer dynamics. There will be many sections under this because this is a very long set of discussion, right? That's what we are going to do. What I will do is I will introduce the basic concepts in the beginning, and then we will specialize to flexible polymers under different conditions in solution and also in melt. And fundamental to understanding polymer dynamics is Brownian motion. So today I'm going to talk about, first, let me introduce the problem of Brownian motion. This is a topic. I think I have a section number. The section number, I believe, is 35, I think. That's my section number. So under this category, I'm going to talk about Brownian motion. Understanding Brownian motion is extremely important to understand polymer dynamics, or for that matter, dynamics of colloids, dynamics of anything that you want to talk about. Right? So in the first today and also the beginning of next lecture, I'm going to focus on this situation. That is, I take a particle, a rigid particle, is not a chain like this. Okay, I'll come to that later on. Right now, I'm talking about rigid particle of mass m and radius r. Spherical particle. Put in a liquid. These are solvent molecules. This is solvent. And let's say the viscosity of the solvent is eta 0. That's the viscosity of the solvent. Now let me ask the following question. What is the velocity of this particle at time t? This is velocity of the particle, of the spherical particle at time t. Right? We write Newton's equation. Right? Force is equal to mass times acceleration. Right? M is mass. Acceleration is the dv t by dt. This is the inertia, right? Inertia term. Mass times acceleration, that's equal to the force, net force. Net force is, there's going to be friction. right? First of all, against the fluid. So let me write the friction to be negative zeta Vt. This is friction. And the zeta is friction coefficient for that particle. Plus any force I'll have on it. There could be gravity, it could be coming from the solvent, bombarding on this particle, on the surface of this particle. It could be anything, right? And we'll work out various situations. We'll work out a situation where force is constant. Force is not a constant because when the molecules come and hit the particle, the force would be random. Right. First, let me look at the force being constant. Okay. If force at time t is a constant, suppose, and then you can solve this, right? Because there's a simple linear equation, dv by dt, right? And then v plus a constant term. You can, the usual technique of solving partial differential equations. What you get is, let me look at the x component. V is a vector, right, f. So let me look at, for the x component, instead of writing a complicated expression for the x component. That means in the Cartesian coordinates, I'm writing x, y, and z, 3 coordinates, orthogonal directions. For the x component, I can solve this equation. That will give me v, right, vx. That's the x component at time t is equal to the force along the x component divided by zeta is a friction coefficient plus v0x. v0 is initial velocity. Okay, v0 is initial velocity, but v0x is the x component of the initial velocity minus fx by zeta times e to the minus zeta t over m. That's the way it turns out. This is a simple solution. I don't believe I have to derive this for you. Now you can look up your earlier notes in elementary calculus. That's what that is. Now, consider the situation where there is no force. Okay, and that's trivial. If there is no force, then this is simply your first order reaction kinetics. dV by dt is proportional to V. We did this in spiral decomposition also. We had same equation, right? So you can solve that. And that's what happens here. When fx is equal to 0, this term goes away, this term goes away. So I have v0x times that. Okay, so that means for fx is equal to 0, I'm not putting any force, right? I drop this particle in the solvent, right? And then I don't have any gravitational force, anything like that, right? Just I have a beaker of a liquid and I put a big colloidal particle, uncharged colloidal particle. So if fx equal to 0, that is external force that we're putting is equal to 0, so what we get is a v t, I can do this in general now, that's equal to v at earlier time, which I'll write it as 0, e to the minus zeta by mt. This is basically the solution of this equation. If this is equal to 0, dv by dt, bring m downstairs here, minus zeta over m, and then, first order simple exponential law, you calculate this, but an initial condition that the velocity is 0, v0. Velocity is v0 at the initial time, t is equal to 0. So that's the solution. So let's plot this, right? You may think that why am I doing this? This is so trivial, right? You will see in the next lecture why this is interesting. V, right, as a function of any component, you can look at the t, right? It's exponential. This is v0 there, and it's exponential, coming like this. Initially, it has some velocity v, but due to friction, right, the velocity becomes smaller and smaller because as a function of t, the particle is experiencing friction against this particular boat, against the fluid, right? This boat is coming down. It's undergoing friction against the background. We can figure this out in a much more easier way by looking at the displacement. As you folks know, the position of this particle, the center of mass of the position of this particle at time t minus position of this particle at earlier time 0, what is this? This is equal to integral, right, v t prime 0 to t dt prime. Right? If I integrate the velocity over a period of time, then I'll get a displacement. So you take this exponential term, put it back in here, except now this expression is for t prime, do that exponential integral. What do you get is this is equal to v0, right, m over zeta, simple integral, exponential integral, 1 minus e to the minus zeta over m times t. It's exact. This is Newton, right? Hundreds of years old. So displacement is given by this formula. Imagine, okay, now let's look at t is equal to very small. Let's look at this situation. This is the displacement for t small. Okay. For t small, we can expand this quantity, right? E to the minus small number. That will give me v0 m over zeta 1 minus 1 minus zeta over m t, and then higher order terms, dot, dot, dot. Okay, so now this 1 and minus 1, this 1 and this 1 will cancel out. I have negative sign here, that's zeta over m. That will cancel out with this term. This and that will cancel out. So what I get now is v0 t. That's equal to displacement. Of course, I have a car, I have an initial velocity, right? And then for very short times without I'm not feeling the friction, right? The velocity times the time is a displacement, right? Velocity times the time is a displacement. Or velocity by definition is displacement divided by time. Okay, that's what we see for short times. For t large, what do you see? For t large, displacement r of t minus r of 0 is what? You can work it out, right? So t is very large, e to the minus t is a large number, e to the minus t is a 0, goes away. So this negative term is a 0. Therefore, the displacement is simply v0 times m divided by zeta. There is no time difference here. For large enough t, the displacement is given by v0, initial velocity, mass of my car, and friction coefficient on the road. Okay, this is Newtonian dynamics, right? Therefore, if I were to plot, now I want to plot I'm sorry, if I want to plot V, displacement. Let me plot R of t minus R of 0. Suppose I want to plot displacement as a function of t. In the beginning, at very short times, right, it goes like t. Okay, so it goes like, it's linear. And then the slope of this is V0, right? It goes like t, displacement goes like t, and the slope is equal to V0, the velocity. But at a long times, what happens is this is a number, right? It doesn't depend upon t. So what happens is for large numbers, large temperature, it saturates like this. Therefore, what I get is, if I plot that curve, it'll look like this. Initially, it'll be linear for short times, but very long times, this displacement does not change with time. And that value, right, is given by these guys, right? I'm already telling you, this is V0 m by zeta. And in here, the slope, that slope is V0. So what I get is, I get immobility, right? The particle now is not mobile. This means immobile. Doesn't move, comes to a halt. Right. Now you should be asking me the following question. What do you mean by time small and time large? Right? That depends on your mass and friction coefficient. As you look at this exponential, there is a characteristic time, right? E to the minus zeta over mt. That means I could rewrite this to be t divided by tau. Okay, this means there is a characteristic time tau, which goes like m over zeta. Because this can be written to be m over zeta, which also comes out in a dimensionless argument. Here, I don't have anything here. I bring m downstairs here. dv by dt is equal to minus zeta over m. And the numerator, I have v. The denominator, I have the unit of time. So I could recognize this to be a unit of time. That would be m over zeta. So right away, as soon as you write the equation, by the shape of the equation, you can tell what the characteristic time is. That characteristic time is m over zeta, and that's what turns out to be here. I can rewrite this to be, this one to be e to the minus t over tau, for example, right? That term. And therefore, tau is m over zeta. So when I say time small, that is with respect to that tau, because this expansion, that is small, means t over tau. Only when t is smaller than tau, I can do this expansion. So that tau is m over zeta, right? Now, for large t compared to tau, then I get into this limit because now t is larger than tau, because this becomes essentially 0. Okay. So in this picture, then the crossover region, right? In this picture, the crossover region is your tau. That's m over zeta. If t is shorter than this, I'll have this behavior. If t is longer than this, I see immobility of the particle. The particle will stop. So this was the situation that we were familiar with for centuries, because this is normal, right? Now let's see what happens in real world. In real world, I'll share with you a simple experiment, which all of us can do routinely now, but this won a Nobel Prize for somebody having fun. All right. This is an experiment done in 1907, around that period of time. It was published in this booklet. I took it from a small booklet. The title of the booklet is Atoms, 1909. The experiment is like this. You put some particles, right? And the particles are roughly half a micron, right? The particles were half a micron, and therefore you can see it with a microscope, very simple optical microscope, not fancy TEM, et cetera, right? This is an optical microscope. And then this gentleman, Perron, what he did was he was was having fun, right? He looked through the microscope and he found where the particle is. And then on a graph sheet with a grid of 3.2 micron scale, he noted it down with his pencil, noted it down where the position of this particle is. And what he found was the particle would be here, and then 30 seconds later, 30 seconds is a long time, right? Right? 30 seconds later, it will be somewhere else. And then 30 seconds later, somewhere else, right? And then he made the trajectories of this particle. And then what he found is a very profound statement. He said, a visible denser object in his suspension, he put a lot of stuff there, a visible with your eyes, right? Visible denser object always ends at the bottom of the vessel. Okay, if there's really a big object, a dense object, like a steel ball or something very dense, it settles down to the bottom of the vessel. And that does not tend to again to raise. It doesn't come up. When you put a steel ball, it goes down and settles there. It's not going to come up. However, fine particles of size like a half a micron, they go, stop. See, they go, stop, start again, then start again, mount, go up, and then come down, and then go up again, mount again, without in the least tending toward immobility. Okay, this argument we made is not seen. Right? This is immobile. We expect this. This is not seen. It keeps on going. Instead of this, right? This is Perron's experiment, right? Instead of this one, this guy keeps on growing like that. Keeps moving around. Mean square. Now, the displacement, right? We monitor this. This keeps going, right? So this is clearly a violation of the dogma of immobility for fine particles of micron-sized particles, or even smaller, or even bigger, as long as they are not dense to sediment down, right? So that created a new way of thinking. In fact, the theory was done even before Perron's experiment, right, which we'll talk about. And let me introduce what is going on. What's going on in here? The introduction is this. Remember, I took this force to be a constant in deriving this law of immobility. What I have to do is realize the realistic situation where the solvent molecules are bombarding this particle constantly. One small tiny molecule hits this, and some force compared to the size of this molecule and force that is generated is a tiny. Right? And then it hits and comes back. Another molecule comes and hits here, goes away. Another one comes and hits it. So the force is not a constant force. The force is random. Right? So we need to think about how to deal with this random force. So let me rewrite my equation once more. So what is the resolution? So I write m dv by dt, right, is equal to minus zeta vt plus this ft I wrote down now is random. This is random force. Okay, due to perpetual collision. Perpetual collision by solvent molecules. So if I were to draw this f of t, some component, say, along t, right? This is going to be, right? It's some, let me write down. This is going to be fluctuating like this. This is random force. 0, plus, minus. It's highly fluctuating. It's noisy because, you know, the solvent molecules are not getting together and decide to hit the particle together. They individually, they act on the particle, therefore the force is going to be random. So if it's a random force, right, then how is that going to be velocity? How is that going to be, how are we going to solve velocity? Unlike the Newtonian case where this was a constant, we could solve it. But for V, we cannot solve it, right? Because for every value, I'll have one value of V. And then another value of F, I'm going to have different value of V. So I will not have a unique value of V. I can define, similarly, in response to this, what will happen is, suppose I want to plot velocity as a function of time, right? There will be maybe some average velocity here, and then this is going to be fluctuating. This will be fluctuating like this, right? So we will worry about how this happens, right? So there will be some average value here. This is average V. We'll talk about what that average is. And then above that average, the velocity would be fluctuating in response to this random force. So this average velocity I will define, or average of anything, I will define to be velocity at local time, particular time, which is, right, which is going to be fluctuating. And I will integrate out this dt over a period of time, t0, some initial time plus some duration tau, sorry, initial time. So I start my clock at t0, and then I wait for some duration tau, t0 over tau, and then divide by tau. Over a period of time, I keep on making the measurement, right? And then I accumulate all this data and divide by the duration. And in the limit, tau becomes large enough, I define my average. This is the time average. Only in that sense I can define. So if I want to solve this equation, I can solve this equation, right? This equation, solve this equation only in some average sense. Only in some average sense. Not deterministically. The way we solve this equation is exact, right? This solution is exact. Deterministic. We can't do that when the force is random. We can define only in terms of an average sense. That's what we can do. So here, the important questions are, what is the magnitude of this fluctuation? Magnitude of this, fluctuation or amplitude. How much it fluctuates, and what is the correlation length? Velocity correlation. What is that? These are the two questions that are important. Amplitude of fluctuation and the correlation length. So in the next lecture, we are going to talk about how we are going to do treatment of particle, Brownian particle, which undergoes bombardment against the solid molecules, which are creating a random force. Okay, there's a friction, there's also random force. This is what we are going to talk about in the next lecture. Right? And this is a foundation. What we are going to do is a foundation for all dynamical processes, not only in polymer science, but also in soft matter physics and biological physics. Okay. I think maybe I should stop here.